We'll now conclude by talking about pH. We learned about the hydrogen ion and the hydronium ion in the previous section, and you saw those were values. For example, the values look like, just to recall, we can say 5.2, 10 to the power -3. And if I ask you if this solution that has, for example, this is the H3O value of the solution of the hydrogen ion, is this acidic or basic? It's kind of very hard to depict with these values. So now a scale has been designed which is called as the pH scale, which stands for partial hydrogen ion concentration of a solution. And the pH scale indicates the acidity of a solution. It indicates whether the solution is acidic or basic. The range is from 0 to 14, where 7 is the midpoint and 7 is the neutral point, which is the midpoint. Values that are greater than 7, that is towards 14, are bases, and values that are less than 7 towards 0 are acids. So we have a scale that is easy to read once we can interplange this value into a normal whole number. Now, pH can also be measured by some gadgets that are called as pH meter, that is shown in this picture. Electronic electrodes are stuck into a solution. It just digitally reads it. There are also pH papers, and you may have used that in classes in biology or chemistry. It has a little index that you can, color change will indicate as to which closest pH that solution is. And the last one is a color test, in which again you can see the different pH. And some of you who have pools may be using either the paper or the color test for that. Definitely the pH meter would be more accurate in a laboratory setting. Okay, now the pH scale is the definition that I gave you previously, which is the partial hydrogen ion concentration, is converted into a mathematical expression, and the mathematical expression is read as negative log of the hydronium ion concentration. Word negative log hydronium ion concentration, because notice the hydrogen ions are present in the square brackets. So for example, a solution which has a value of 1 into 10 to the power -14, let's go ahead and again play with our calculator to see how to determine the pH. Again, we are going to use scientific calculators for this purpose. Let's see, I don't think you are able to see the whole thing, because I'm going to go ahead and put it over here in the center so you can see. So now the first thing you want to look for is a key that is called as the pH key, the log key, which is here. And let's look back. We have negative log of 1 into 10 to the 4. Now, I'm going to try doing it 2 different ways. It depends on which calculator you have. You can either say negative 1, as a matter of fact, sorry. The value was 1 into 10 negative 14. 1.0 exponent -14 and hit log. And there is a value of -14. Now this, in order to get rid of the negative sign, it is then multiplied by -1 to give you a positive value, which is 14. Now I don't know why didn't it do that over here. Maybe I needed to put the negative before. Now this is because some calculators are just a little different. They are kind of floaty. So let's say, okay, we got that. That's probably why. So again, you go ahead and put in the value like 1.0 exponent -4. The log is, did I do 14 or did I do 4? It should be coming out as 4. Okay, hang on. 1.0 exponent -4. Yes. And the log, I forgot to hit log. There it is. It's -4, and if you multiply -4 by another -1, it will give you a positive value. So the purpose of using the pH in this mathematical expression is to get rid of the negative and also to determine its pH. So let's look at some other problems that I have solved in here to see if we can get to it. We'll go ahead and play with this value here, which is a 1 into 10 to the power negative 3. Again, 1.0 exponent negative 3, hit log, and you get the value, which is negative 3. You multiply that value by another negative sign to get rid of the value to give you a 3. Now that the pH is 3, you can now look at this chart over here and determine that if the pH is 3, then this solution is going to be more acidic. So now that value of the hydrogen ions and the OH ions that we have been determining are interpolated into a sensible value, which will then give you a choice whether you have an acidic solution or a basic solution. Now we're coming to almost at the end, which is, as a matter of fact, why don't I go and give you another example on the previous one. Let's try to put in the value of, for example, a value of 5.0 10 to the power negative 4. And I want you to show you how to put this value in, which is 5.0 10 to the power negative 4. So now I'm going to go and put 5.0. Okay, 5.0. Actually, I did. My little gadget sometimes gives me trouble. Okay, so 5.0 exponent negative 4, and we hit log. So now we're getting a value which says 3.3, and this you can skip all the rest of the values. Just go with the first 2 digits, 1 digit or 2 digits beyond the decimal point. The value that's coming is 3.3, and if you multiply that by another negative 1, the pH of a solution that has this value would be 3.3, and that would be an acidic solution. So we'll do more practice with these in class too, but just in case if you're having some trouble at home, I wanted you to review how to use a calculator. The last section is also very important, and that is the concept of neutralization. Neutralization is when an acid reacts with a base to produce what is called a salt and water. By this word salt, I'm not just talking about sodium chloride. It would be the cation-anion combination. So for example, if we take HCl with water, now what will happen is we have the sodium, we have, actually, I'm going to bring in here this. Okay, the reaction that we're trying to see is HCl with the base over here that you can see at the end over here. And this reaction is shown that if you take acids by themselves, you take these acids, this acid is reacting in water as the hydronium ions and the chloride ions, and the sodium hydroxide, which is a base, is reacting in water to release the sodium ion and the OH ion. Now, once we have 2 kinds of ions in water, the next thing that's going to happen is the ions are going to interchange. So the sodium ion is going to form with its counter anion to give you what is called as the salt, and the other 2 are always going to give you a water molecule. So regardless of what acid or which base are we using, you always take the anion from the acid, which is here, and the cation from the base to put them together as sodium chloride. So for example, on the same reaction, if I was to change, instead of HCl, if I was to put down, for example, HNO3, what will happen now? You would, instead of the chloride ion, you would have a formula of NaNO3, which would be sodium nitrate. And that would be called as the salt that is formed by the cation and the anion. Cation is coming from the base, the anion is coming from the acids. There is another example of a neutralization reaction in which you can see how it was balanced. You can see a reaction of magnesium hydroxide with nitric acid is showing you that one of the substances is always going to be water, and the other is going to be the magnesium cation and the nitrate anion to give you this comfort. I'm probably going to give you one of these in the test for sure. So if you get any kind of reaction that says what is going to happen between magnesium hydroxide and nitrate, I want you to think about it. You know that magnesium and nitrate are the cation and the anion. So you just can't write MgNO3 and water. What's wrong with this reaction? What's wrong is that we did learn a long time back how to write compounds and their formulas. Reflect back to see if the formula of magnesium nitrate is correct. Notice there's a 2 over here, which indicates that the magnesium ion has ionic charge of 2 plus. And notice what is the charge of nitrate. It seems that it is 1. Actually, I should get rid of the hydrogen. I should put down the nitrate. Okay, so the nitrate is 1 negative over here. So now when I cross these two out, the formula should be MgNO3 2 plus H2O. Once you have that formula of the compound, then you have to go back and balance them. So for me to test you on a final, it's very easy. I can give you one of these balancing reactions between any acid and a base and see that, do you remember how to write down formulas? Do you remember how to balance them? And do you remember what a neutralization is? So we have 3 different concepts that we learned over the semester that can be applied to one simple equation. So do practice with these. I will practice with you in class on these 2. Be sure there will be 1 or 2 equations that will be like this, and learn how to find the ionic charge, or learn the trick how to determine the ionic charge from the formula from the periodic table. You should have to memorize any of this stuff. Okay, so lastly, we'll just touch base with the term buffers. Buffers are solutions of weak acids and weak bases, and it's a solution that has both kinds of ions, and it will resist a change in acid or base to a solution. Now, the changes that it affects are usually in a narrow range. So, for example, buffers in blood, if the pH is 6.4, and if the solution is acidic or basic added to the blood cell, let's say 6.7, which would mean that it's a slightly more basic solution, buffers can resist by adding acids to this medium to lower down the pH. On the other hand, if the pH goes lower, it can release the OH ions to make it more acidic. So buffers are solutions that resist a pH change. So this concludes our section of acids and bases, and we have pretty much finished the inorganic section of our lectures, and we will then begin the organic section.